Use the divergence theorem to evaluate the surface integral of f dot ds, where our vector field of xyz is defined by x cubed plus y cubed plus z cubed, x cubed plus z cubed, and where S is the sphere with the center of the origin and radius 3. So first and foremost, let's always draw a picture of our surface. A sphere with the radius of the center of the origin, as always, let's start drawing our problem so we can visualize what we are doing. So let's draw our sphere pretty roughly. It doesn't need to be perfect. We just need to see what our surface looks like. Recall that the divergence theorem is just the triple integral of our surface of the divergence of our vector field. So let's start defining what our bounds for our integrals are going to be. Because it's a sphere, let's use spherical coordinates. We know that our rho value is going to go from 0 to 3 because our radius is 3. We also know that our phi value goes from 0 to pi because it's a complete circle, and then our theta value will go from 0 to 2 pi. So we can set up our bounds just like so, from 0 to 2 pi, 0 to pi, 0 to 3, with our integrand still being the divergence of our vector field. So our divergence of our vector field is going to be equal to the del operator times our vector field. The partial derivative of our first component with respect to x is going to be equal to 3x squared. Our second partial derivative with respect to y for our second component will be 3y squared, and the partial derivative with respect to z of our last component will be 3z squared. Because we're using spherical coordinates, we can recognize that 3x squared plus 3y squared plus 3z squared is just going to simplify to 3 rho squared. Now, if we set up our triple integral from 0 to 2 pi, 0 to pi, and 0 to 3 of 3 rho squared, and don't forget our Jacobian for the spherical coordinate system, which is just rho squared times sine phi. And then, of course, we have our d rho, d phi, d theta. Let's simplify the integrand. So we're just left with 3 rho to the 4th power sine phi d rho d phi d theta. Let's start by taking out the constant 3. So we're left with just the 0 to 2 pi, 0 to pi, 0 to 3, and rho to the 4th times sine phi. Because our integrand has no values that depend on each other, we can separate them to make it a little bit easier to evaluate. So we'll have 3 times the integral of 0 to 2 pi d theta times the integral of 0 to pi sine phi d phi times the integral of 0 to 3 of rho to the 4th d rho. Now, by evaluating this, we have 3 times theta from 0 to 2 pi, because the integral of 1 with respect to theta is just theta, times the integral of sine phi d phi, which is just negative cosine phi, from 0 to pi times rho to the 5th over 5 from 0 to 3. Let's begin to evaluate this further. So we have 3 on the outside still. Theta from 0 to 2 pi is just going to be 2 pi. And then negative cosine from 0 to pi is going to be negative 1 plus 1. And then, of course, we'll just have 3 to the 5th over 5. Let's continue to simplify. We'll get 6 pi times 2 times 243 over 5. And lastly, combining everything, we'll get 2,916 pi over 5.